Hello there. Man, I'm especially tired this morning. Wait about one more minute.
Mr. Bugs.
All right, so I think I'm going to go ahead and get started. Good morning, everyone. So, for the last 3 lessons, we got a little taste of scientific computing and what that could be like. And so there's another topic that I think is interesting that I thought I would teach you guys about, and it's the topic of machine learning. So how do you teach a machine to do something? Um, and so we're going to be focusing on pattern recognition with something called a neural network. So you might have heard that word before, neural network. And so over the next 3 or 4 lessons, maybe, I'm going to be trying to teach you what a neural network is. Okay, so this is going to be mostly theoretical kind of lessons. So I don't need to do any coding, but then you guys are going to implement the theory that I'm going to develop into code, so that you can have a neural network that actually does something useful. Okay. So let's go ahead and get started. So today's lesson is the first of a couple of them about neural networks. Okay. So one of the things about neural networks is that they have a node. They have what are called nodes or neurons. Okay, nodes, or also known as neurons. Okay, so we're going to represent a node as a circle. Okay, and that node is going to have an output. Okay, and it's going to have several inputs. Okay. So in this case, we have a neuron with 3 inputs. And then each of these inputs is going to be a double, and the output is going to be a double. So maybe the three inputs are let's say 0.1, negative 0.5, and 0.9. Okay, so what the neuron is going to do is it's going to take all of these inputs and add them together. Okay, so there's a total input to the neuron. So no matter how many it has, it could have 85 inputs into it. It just takes all those and it adds them up. So if I add those three numbers up, I would get negative 0.4 plus 0.9. I would get plus 0.5. All right. So it combines those, and then it applies what is called the sigmoid function to it. So we're going to define a function. It is called sigmoid, but I'll just call it sig of x is equal to 1 over 1 minus e to the negative x. Oops, am I goofing with what this? No, I've got it right, don't I? Let me just double check. Yeah, okay, I got it right. So yeah, so what we would do is we would apply the sigmoid function to 0.5. So sig of 0.5 is going to be 1 over 1 minus e. No, I didn't get it right. I'm sorry, guys. That's what I thought. This should be a plus. So this is the definition of sigmoid. So that would be 1 over 1 plus e to the negative 0.5. And so by e, I mean the transcendental number 2.71, blah, blah, blah. Okay? So if I do that, so I have to do e to the negative 5 plus 1. And I get 0.62. Okay? So that means that the output of this neuron is going to be 0.62. All right? So what the neuron does is it sums the inputs. Okay? And then it applies the sigmoid function to it to get an output. Okay? So if we were to graph the sigmoid function, here's what it looks like. So you have an output. All right. And then you have an input. Here's 1. Okay. So this is like the y-axis and the x-axis here. And so if the input is small, the output is small. And if the input is big, the output grows to a maximum of 1. Okay? And so this is actually, so it's like there's a threshold, if you will. Okay? Once the input is past a certain threshold, the output is basically going to be 1. And so this is how actual neurons, like in your brain, work. Okay, they have inputs to them, and if the input is big enough, then the neuron decides, okay, I'm going to fire, and it sends that output further through the network. Okay, so this is the idea, is that if the input to that neuron is too small, then the output is going to be small and it's not going to pass it forward. Okay, so this is how neurons are observed to behave in nature. And so the idea behind a neural network is to have it be built up out of objects that behave similar to actual neurons, okay, to try and imitate the human process of learning. So the other thing we have to talk about is what are called synaptic weights. So this link, these links are called synapses, all right? Just like actual neurons are connected through little filaments that are called synapses. And so we have these things called synaptic weights, which, okay, so maybe a neuron has 2 inputs. Let's make it 2 inputs for this neuron. And it has an output. So maybe this input is 0.8, and this input is negative 0.9. Okay? The idea is that each connection into a neuron has its own strength. So maybe the strength of this connection is 1.0. And so this is a synaptic weight. And this one has a connection of, let's say, 0.2. All right? So this synaptic weight is larger than that synaptic weight. So what that means is that this input signal is going to get priority over that input signal. So in other words, this signal is more important to the function of the neuron than that input signal because it has a bigger, this one has a bigger weight. So all these weights do is they multiply the input. So what that means is that the input is going to be 0.8 times 1.0, so that input gets multiplied by its weight. All right. Plus, and then this input gets multiplied by its weight. So you would have negative 0.9 times 0.2. Okay, so that's 0.8 minus 0.18, so that would be what? 0.62. All right. So that means that the actual input is 0.62, which then the sigmoid function is applied to that. Okay, so we would have 1 over 1 plus e to the negative 0.62. And that is 0.65, and so the output of that neuron will be 0.65. Okay? So let's talk about, so what we've focused on so far is a single neuron, okay? But let's look at the neural network as a whole, okay? So the overall look of a neural network, okay? So you have a number of nodes of neurons, okay? And then maybe you have another, and then, okay, so this is a, so we got inputs, bam, 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 bam. Bam. Okay. So what we have here, this is a picture of a neural network. So this is a so-called 3-4-2 neural network. Okay. So it has basically the nodes are arranged in layers. Okay. So this would be layer 0. This would be layer 1. And this would be layer 2. Okay, so layer 0 has 3 neurons in it. Layer 1 has 1, 2, 3, 4 neurons in it. And layer 2 has 1, 2 neurons in it. So that's why it's 3, 4, 2. Okay, and so what you can see is that each neuron has synapses that lead into the next layer. So this neuron has 4 synapses that lead into the neurons in the next layers. Okay, and so we have an input signal. So we have an input, and then the input gets fed through the synaptic weights into the next layer, and then the sigmoid function is applied to it, and then it gets passed on to the next layer. So the information that goes into the neural network goes layer by layer by layer until it reaches the output. All right. Now, you could have, so like maybe you have a, I don't know, what if you had an image that was, let's say, 1024 pixels, okay? And you want to know, so you have an image that is 1024 pixels, all right? And you want to know, is it a dog? Is it the image of a dog? This is the kind of question that a neural network can actually answer. It's pretty cool. What you would have is in your layer 0, you would have 1024 neurons. Okay, so each pixel, maybe the brightness of that pixel is an input to one of the neurons, and then it has a number of layers. Maybe, I don't know, it goes to 100 neuron layer, and then maybe that goes to I don't know, a 20 neuron layer, and then maybe that goes to a 1 neuron layer. Okay? So what happens is the output signal, there's only, in the output layer, there's only going to be 1 neuron. And if that output is greater than 0.5, for example, you would conclude that it's a dog. All right, so if it's, or at least the neural network thinks it's a dog. If it's less than 0.5, the neural network does not think it's a dog. Okay, so you can have a neural network that takes in inputs and then you look at the output, and that's a decision that the neural network has made. Okay, so I have a neural network that I drew here. Okay, and so this is has 3 layers: layer 0, layer 1, layer 2, and each layer has 3 neurons. Okay, and so what we're going to do is we're going to see what is the output of the neural network if it has 3 inputs of 0.9, 0.1, and 0.8. Okay? So let's see how that would look. So the first layer passes the input into the network. So the first layer basically doesn't, oops, that wasn't even visible. The first layer passes the input into the network. It doesn't do anything. In other words, it doesn't apply the sigmoid function to it. Okay, so here's what we're going to get. So let's look at this neuron right here. Okay, what is this neuron's input going to be from this neuron in the previous layer? Okay, it's going to be 0.9 for this input times the synaptic weight, which is also 0.9. Okay. From right here, this synapse, it's going to be 0.1, which was the input here, times the synaptic weight, which is 0.3. Okay. And then the last input to this neuron is from this neuron. So the input is 0.8, and then the synaptic weight is 0.4. So I have 0.8 times 0.4. Okay, so I'm going to add all those up. 0.9 times 0.9 plus, so here's what I'm doing in my calculator. I'm doing 0.9 times 0.9 plus 0.1 times 0.3, because this weight was 0.3, plus 0.8 times the synaptic weight, which is 0.4, equals, so let me work that out. So that's 1.16 is the input to that neuron, okay? And then the neuron applies the sigmoid function to that. So I have 1 over 1 plus e to the 1.16 is going to be the output of that neuron, Okay, so I have 1 plus e 1.16. Oh, that should be, sorry, that should be negative 1.16. And so the output is 0.76. Okay. So that's the output of this neuron. So now what I'm going to do is I'm going to do the same thing, but for this neuron. And then I'm going to do the same thing, but for this neuron. So this neuron has synaptic weights that are 0.2, 0.8, and 0.2. So that 0.2, so this synaptic weight, the 0.9 is going to be multiplied by 0.2. Okay. Here, the 0.1 is going to be multiplied by 0.8. And here, this 0.8 input is going to be multiplied by 0.2, which is the synaptic weight for this link. Hopefully you can see why it's advantageous to do this with computers, because it's very tedious. Okay, so I got that the input is 0.42. Okay, and then I have to apply the sigmoid function to that. And I get 0.60 is the output of this neuron. Okay. Then I have to do the same thing for this one. Okay. So the 0.9 gets multiplied by 0.1. That's the synaptic weight for this link. Then the 0.1 gets multiplied by this synaptic weight, which is 0.5. The 0.8 gets multiplied by this synaptic weight, which is 0.6. Okay, so going through that again, we get 0.65. Okay, so now we have one more layer to go. So now the input of this middle layer, or sorry, the output of this middle layer becomes the input of the last layer. Okay, so this 0.76 gets multiplied by 0.3 for that link weight. This 0.60 gets multiplied by 0.7 for that link weight. This 0.65 output gets multiplied by its weight, which is 0.5. Okay. 0.76 gets multiplied by this weight, which is 0.6. 0.6 gets multiplied by 0.5, which is that weight. 0.65 gets multiplied by this weight. Okay. Then for this last one, 0.76 gets multiplied by 0.8. 0.6 gets multiplied by 0.1. 0.65 gets multiplied by 0.9. Okay, so I just did all of the, so now I'm going to actually do these computations and add them up to get the input to the final layer. So this one has an input of 0.97. By the way, link weights can be negative. So I've drawn all of them as positive, but they can also be negative. This one has an input of 0.89. And this one has an input of 1.25. So now once I have those inputs, I apply the sigmoid function to them. So I'm going to do 1 over 1 plus e to the negative 0.97. And that's going to be the output of this neuron. Okay, so 1 over 1 plus e to the negative 0.97. That gives me 0.72 is this output. And then for this neural network, I have an input, or for this neuron, I have an input of 0.89. So this one has an output of 0.71. And then for this last one, it has an input of 1.25. Okay, so we have 1.25. And this one is 0.78. All right, so what I've just shown you is how a signal, how an input signal is converted by a neural network to an output signal. So if the input is 0.9, 0.1, 0.8, then the output is 0.72, 0.71, 0.78. All right? But what I want to do is I want to talk just a little bit more abstractly about, so that I can get you a general formula. Okay? So a bit more abstractly. All right. So we are going to have a number of layers. So I will call this layer 0. I will call this layer 1. So I'm not drawing the individual neurons. Okay. This is layer 2. And I don't know how many layers there are. This is layer n minus 1. Okay. So this means that there are n layers total. Okay, because in programming we start out with 0. And it goes up to n minus 1. All right. And let's suppose that there are a certain number of neurons in each layer. Okay. So if we looked at one of the neurons, all right, let's suppose that this is neuron J in layer 1. Okay. Then I'm going to introduce some notation to get the for the link weights. Okay, so the notation that I'm going to introduce is W, IJ, and then parentheses K. All right. So what does this mean? It means this is the weight of neuron I in layer K to neuron J in layer K plus 1. All right. So, so for example, let's suppose that this is neuron 4, all right, and this is neuron 9 in layer 0. This link weight is going from neuron 9 in one layer to neuron 4 in the next layer, okay? So this would be, the link weight would be W94, and it's going out of layer 0, so I would have parentheses 0 up there. All right. Maybe we have neuron 42 in layer 1 connects to neuron 78 in layer 2. So this link weight that connects those two would be W42 to 78, and it starts in layer 1, so I would put parentheses 1 up above it. Okay? So that's how the notation for link weights works. Okay? So if we think about it, oh, and then I'm also going to introduce the following notation. O parentheses K sub I is equal to the output of neuron I in layer K. All right. So if we think about it, so now what I want to do is I want to write a formula for what we were doing here. Okay. I want to write a formula for what we were doing here. So let's suppose we want to get the output of neuron I in layer K. What is the formula for that? Well, we have to remember that the output has the sigmoid function applied to it. Okay? So the output is going to be the sigmoid of something. Okay? It's going to be the sigmoid of the input signal. Okay? So now the question is, what is the input signal? Well, the input is the sum of the outputs of the previous layer multiplied by the weights, the link weight. Okay, so how could we express that? Well, what are all of the neurons that link in to node I? Okay, so we would have the output. I'm just going to write it out and then explain it. That'll be easier. Okay, So this is the correct answer for the input signal. So what does this mean? Well, so what does this mean? We are taking the output from neuron J in the previous layer. See how it's not K, it's K minus 1. So the previous layer, we are multiplying it by the link weight, because this is the link weight that connects neuron J to neuron I, so it's WJI, and it's the link weight that is coming out of the previous layer, okay? And we are summing over all of the neurons in the previous layer. So this is our main formula for today. All right. So what it says is that the output of a neuron I, in layer K, is the sigmoid function applied to the outputs of the previous layer, because it's K minus 1, multiplied by the weights in the previous layer that connect into neuron I, and then we're summing over all of those, okay? So what you guys are going to do is you're going to basically implement this equation in code today. And then we'll continue learning more about neural networks on Thursday. So that is my lesson for